The preceding lecture covered the statistics used to describe the results from a sample. In this lecture, I'm going to cover the statistics used to assess specific questions that can be framed as hypotheses. Most of these hypotheses are about differences between groups or differences between conditions. Now I turn to the more complicated situation addressing hypotheses that involve more than one variable. So two variables, bivariate analyses. These are tests of hypothesized differences involving two variables. Typically, it's a comparison of groups defined by different levels of one variable, for example, males versus females, on a second variable. So, for example, a comparison of the heights of men and women would be a bivariate analysis test. So when comparing two means with independent samples, that is, the test of the equivalence of means from two groups that are unrelated, two groups with one measure. So you're taking men and women, two groups, or you're taking people in Washington and people in Oregon, two separate groups, or you're comparing people who buy the brand with people who don't buy the brand, two separate groups. And in every case, you're asking them the same question or taking the same measure. So that's two groups, one measure. The t-test statistic is defined as, in the numerator, the difference between the sample means, x bar 1 minus x bar 2, and the hypothesized difference in the population means, which is mu1 minus mu2. So you're looking at whether the samples differ more than expected, or how much the samples differ relative to what's expected, and comparing that again to the standard error of the mean. And the standard error of the mean here is the standard error of the difference between x bar 1 and x bar 2. The full expression of that given here is the t observed is x bar 1 minus x bar 2. Now this presumes that there's no hypothesized difference between the populations, which is normally the case. So mu1 minus mu2 is 0. So the numerator then is simply the difference between the two samples, x bar 1 minus x bar 2. And the denominator is a sort of complicated expression, n minus 1 times s1 squared plus n minus 2 minus 1 times s2 squared. That quantity divided by n1 plus n2 minus 2. And that fraction multiplied by the expression 1 over n1 plus 1 over n2, and then take the square root of that entire thing as the denominator. The degrees of freedom for this t is n minus 2, where n is the total n, that is n1 the size of sample 1 plus n2 the size of sample 2. And this t-test assumes equal variance. That is, the two samples have essentially equal variances. If they have unequal variance, the test can still be done and all statistical packages will adjust for it. Typically what you get is a t-value assuming equal variances and then another t-value for assuming unequal variances. So let me illustrate that bivariate t-test with a problem. First setting it up as a univariate question. have monthly sales of store 1 exceeded the goal. The goal is 19,200, and we've got 9 observations. And across those 9 observations, we observe an average of 20,000 with a standard deviation of 600. So the observed t is x bar minus mu over the standard error of the mean. So we've got 20,000, and the mu hypothesized value is 19,200. So we've got a difference of 800. We calculate t, we see that it's 4.0, and that observed t is greater than the critical value of 1.86. So we would conclude that yes, the store has exceeded the goal. So this is a t-test of a sample versus a point estimate. The sample mean 20,000, the point estimate 19,200. So now we introduce another variable and make this same situation a bivariate analysis. Are the monthly sales of store 1 greater than the monthly sales of store 2? So now we don't have a point estimate. We've got another distribution of scores that represent store 2. So x1 observations remain the same, a mean of 20,000 and a standard deviation of 600. And store 2 has a mean of 19,500 with a standard deviation of 400. So again, we have this complicated expression for the observed t. We've got all the values. We just plug them in. And we test the hypothesis that the mean of 20,000 differs from the mean of 19,500 given the standard deviations in each sample. And we see that the t observed is 2.77, which is greater than the critical value of 1.75. And so we conclude that the sales in store 1 are statistically significantly greater than the sales in store 2. So here's another problem representing independent samples t-test. Compare brand attitudes among purchasers and non-purchasers of Apple products at an alpha of 0.05. So brand attitude is represented or is assessed here with a 7-point scale. Could be anchored bad, good. Could be anchored undesirable, desirable. It could be a combination of 2 or 3 items. So we would have the average score on several differential adjective scales. But for purchasers, we had 30 purchasers. The average score was 6.2 with a standard deviation of 1.1. And for non-purchasers, of whom we had 35, the average attitude score was 5.5 with a standard deviation of 1.2. Again, plugging those values into the expression to calculate the observed t, we get an observed t of 2.43, and we compare that with the critical value of t for 63 degrees of freedom. And notice 63 degrees of freedom is 30 plus 35 minus 2, which at alpha 0.05 is 2.0. So our conclusion would be that, not surprisingly, purchasers of Apple products have a more positive attitude toward Apple products than do non-purchasers of Apple products.